All right, welcome AP 20.3. If you paid really good attention to the lab, this should be easy peasy. Voltaic cells, definitely always a key part of the AP test. So let's begin. What are the learning objectives? As you see, there's quite a few. So number one, can you balance a redox equation using half reactions, which I think we're pretty good at after 20.2. Balanced chemical equations for redox can be constructed from those half equations. So remember the half equations, you actually see the electrons in those half equations. Explain the relationship between a physical component of the electrochemical cell and its operation. So this is why, ladies and gentlemen, the last lab is I wanted to make sure that you saw not only how it operates, but all the parts that go with it, okay? So each component of the electrochemical cell, so where are the electrodes, who are they? The solutions in the half cell, what's the purpose of the salt bridge? And then how is the voltage measured, okay? It's usually a voltmeter. They all play a significant role in the overall functioning of the cell. The operational characteristics of the cell, there's two types of cells. There's a galvanic cell, which is also called voltaic. That's the one I'm used to. Galvanic or electrolytic. Now you're going to see electrolytic, the very last one, chapter 20.9. Okay. Can you explain the direction of flow of electrons? Which reaction is taking place in which cell? The change of the mass of the electrodes, because one electrode will actually lose mass and the other one will gain. The evolution of any gas that comes off those electrodes, and how do the ions flow through the salt bridge, okay? So yes, you probably weren't fabulously happy about doing the last lab, but it doesn't matter because it's very important about how you understand the function of that voltaic cell, okay? Microscopically, particle diagrams, you know you're going to see it, okay? Galvanic sometimes means voltaic, okay? And when you have a galvanic cell, a voltaic cell, we want thermodynamically favored reactions. And we know that the delta G better be negative, okay? So whereas electrolytic cells involve a thermodynamically unfavored reaction, okay? So electrolytic involve not being spontaneous. So that means our delta G would be positive in that case. Visual representation of galvanic and electrolytic are tools of analysis to identify the half reactions involved and which directions the current flow. So we have to figure out which electrons, where the electrons flow from one to the other, the ions, where do they flow, and which half reaction is occurring where. For electrochemical cells, oxidation is always the anode, and the reduction is always the cathode, okay? Because you got a new equation coming your way in 20.4. Explain the relationship between the external sources of energy or coupled reactions. And I know you saw a video, gosh, my mind is going blank, but I know it was in, I want to say Unit 9, where they were doing Hess's Law with delta G. That's what that coupled reaction is, aka Hess's Law, where you have A plus B, maybe goes to C, and you have like a delta H, or you can use delta G. I know in that video they use delta G. And then C makes D and E. And then you have that delta H or delta G value. And then the overall, we would just add up those delta H's or G's. Okay, that's a coupled reaction. How are the coupled reactions? How do they drive the thermodynamically unfavored process? Okay, so unfavorable. And we know unfavorable would mean that delta G would be positive. An external source of energy can be used to make a thermodynamically unfavored process. And examples are electrical energy to drive an electrolytic cell or charging a battery. Okay. Usually right here, a battery, it is a voltaic cell. And what happens is electrolytic cells need a battery. And that's what makes it not thermodynamically favored, because it relies on something to make it work. Just like our cell phones, just like television, just like the computer. We have to charge it up. We rely on energy. We rely on that electricity. We rely on that battery. So electrolytic cells need a battery, which means it's not thermodynamically favored. But like Voltaic cells are batteries. Oops, go away, Microsoft. So they are batteries, okay? Just like light to drive the overall conversion of carbon dioxide to glucose in photosynthesis. So they mention this in our learning objectives. I've never understood why, because it sounds a little bit like a little biology going on there. But in order for carbon dioxide to get converted into glucose, so that's CO2, into that C6H12O6, there must be some type of light that has to drive it, okay? Which means it must not be thermodynamically favored. So not thermodynamically favored because it relies on the light, okay? Never seen a question about that, and I'm not going to spend a lot of time on that. We are going to totally break apart a Voltaic cell, talk about all the different parts, why they're important, and would it function without them, okay? So we need a thermodynamically favored reaction. We need that delta G, because you know there must be a calculation coming somewhere. We need that delta G to be negative, okay? Voltaic or galvanic, doesn't matter to me which one, just as long as you know both names. It's a device in which, definitely a device, in which the electrons transfer through an external current. And usually that external current, it's a wire. It's a piece of wire, okay? Parts of the Voltaic cell, so what I'm going to be doing is I'm going to be going through the notes, and I'm going to be drawing a picture, okay? As you see right here, there's a picture right here, but I don't know if there's going to be enough room for me. So, you know what? I'll just put the picture right down here, okay? All right, so usually we would have, looks kind of like two beakers. And it doesn't have to be beakers. It could be like those spot plates. Remember back in CP and honors where you would have like this white plate or clear plate where we could do like 6, reactions at like the same time. They just look like a little plate like this, and they have like these little circles. And you would just do like whatever chemical reaction in that circle and then do another one over here. We call them spot plates, well plates, okay? We usually use those in the lab, but you could also, when they draw the pictures, they look like beakers, okay? So in here, these are called cells, okay? So we'll just call this cell number 1, and this could be like cell number 2, okay? So in this type of beaker, there is a half reaction happening in here, and there's a half reaction happening in here, okay? So in these cells, this is where the half reactions occur. Okay, and same thing over here, this other half reaction where it occurs. So I'm just going to cells, okay? In here, we would have a piece of metal, okay, on each side. And as you saw in the video, they're like long strips of metals. And let's do some stuff in some different colors. There we go. So what these are called, they're called electrodes. Okay, and electrodes are metals, pieces of metals, okay? Now, you can do a non-metal, but the problem is with non-metals, some of them are gases. So you'll see when we get to about 20.4, what happens if it's like a gas, like chlorine or something, okay? So right now, electrodes, they're a piece of metals, okay? Now, one of these electrodes, one is the anode, and one is a cathode, okay? So I'm just going to call it A and C. Now, what do we know about an anode and a cathode? Well, an anode is where oxidation occurs. And what happens is if oxidation is occurring here, that means that this piece of metal is losing electrons. And you don't ever think of it, ladies and gentlemen, but remember, electrons, they have mass. Very small mass, but they do have mass. And because they have mass when it's losing electrons, what happens is the anode is going to appear to be looking smaller and smaller and smaller. So what happens is to the anode, the mass decreases. I mean, we're not talking a significant amount, but it actually starts to look like it's kind of shrinking. So at the anode, that's where oxidation occurs. So you will never be asked to draw one from scratch, just to ask questions about it. Now these metals, they have to be in a solution. They have to literally be touching the liquid in the beakers, the cells, okay? I always like to label this first one as the anode because I kind of go alphabetical. And then this guy is the cathode. Now remember, for the anode, this is where oxidation occurs, okay? And with that oxidation, we know that the anode, this piece of metal, and actually I want to label it over here, sorry, because I want to label something else at the bottom. So the anode is where oxidation occurs. And what you would see with your half reaction would be the piece of metal, that's a solid, and it loses whatever amount of electrons, okay? And now it's going to go aqueous. Well, then you're like, well, where the heck is this aqueous card? It's in here. It's that guy. What happens is these pieces of solid, okay, all these solids right here, well, the ones that are underneath, they're going to start to come in here. And these pieces of metal, that's a solid, is then going to come into the solution. And that's why the anode over time, it's going to lose not only electrons, but it's going to lose some mass. It's going to get smaller and smaller. And that mass that the metal was, the solid, is going to turn in to this aqueous metal, this aqueous in here. On this side, obviously the cathode, okay, it's just the opposite. So if the anode has to be losing electrons, well, that means the cathode must be gaining them, and that's where reduction is occurring. So the reduction, the metal will be gaining electrons, and what would happen over time, the mass of this electrode will actually increase. And what always stumps students is, well, how did it increase mass if like the piece of metal was like already had a certain mass? How did it gain mass? Well, what happens is the ions that are in the solution will then turn into solids. And we call this, ladies and gentlemen, we call that a precipitate. Okay, when you take a liquid and make it into a solid, we call that a precipitate. Okay, so what happens is over time, it's going to appear a little bit larger. It's because the ions are something called plating. The ions are plating from the solution onto the piece of metal. So what happens is now in this direction, you're going to have, we'll call it capital C. There you go. This capital C, positive ions, they're going to start to plate and form little precipitates on it called solid. So in your half reaction for this one, it looks like the ion now becoming solid form. And because it had already an electron missing, now it's neutral. Okay? And so what happens is you see the electron for the half reaction, the electron appear on the reactant side. Okay? And we just practiced that in 20.2. So the cathode, right here, this is where reduction occurs. So not only will it gain electrons, but it's going to gain some mass. And what mass will it be gaining? It's from this precipitate right here. So on this side, where's the electron? Well, the electron's on this side, okay, on the product side. Okay, I always like this chapter because it's always opposites of each other. If I know one thing, I know the other one. It's just complete opposite. So one of them is losing mass, the other one is gaining mass. One's losing electrons, gaining electrons. Well, there's a very, 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 very important piece that has to connect these two cells together. It's called a salt bridge. And usually this salt bridge, you would see it in the video, could be like a piece of paper that's been soaked in a salt solution. It could look like this kind of U-tube shape type of something. And basically, kind of a little sketch of it, if this is your two cells, it's like a piece of paper. Here's your liquids. And this like piece of paper just kind of drapes over into one beaker to the other. But the key part is it has to be under the liquid, because what happens is all these ions, the pluses and minuses, they're going to travel through one and get to the other side. And you can only do that through a salt bridge, because remember this thing right here, only the electrons are transferring through the wire. Well, how do the ions transfer? The ions are transferring through the salt bridge. Oops, we'll put transfer. So the ions, they are transferring through the salt bridge. So a device used to maintain electrical neutrality, we're trying to get the electrons to balance out. So if you notice down here in our equation, when we do our full equation, we'd have the metal that lost, we're just going to say 1 electron, and produce 1 electron. And then we have our reduction, where it's an electron, our capital C ion, and then our C solid. And that's the part. That's the electrical neutrality. It's not just to get those electrons to cancel from each other, is we need them to be balanced so they do cancel each other out. So electrical neutrality. Okay? If one equation had 2 electrons, the other one had 3, then you'd have to find a common multiple between the two of them. Okay? So in this salt bridge, the salt bridge sometimes could be like a paste or a gel. You may have seen it in that one video where it looks kind of like a glass tube, like a upside down U-shaped tube, and it's got like this paste kind of in it. Think of it like kind of like really thick, kind of waxy type of glue. And inside here, what's going to happen is some of the ions are going to travel through, and some of the ions are going to travel through this way. And the only thing that's traveling through there is only the ions, not electrons. Okay, the electrons are going through the wire. So the major part of this is this cell won't work, and this is where doing this in the lab actually is important, because I would have you guys set this up, and the cruel person that I could be sometime is I wouldn't put out the salt bridge, because I'd be waiting for you to remind me to give you a salt bridge. So you would be doing the experiment and like nothing's happening. The voltmeter saying 0 to the end of time. You're like, Rodriguez, I don't know what I'm doing. I know I did this right. I know I set it up right, but it's like it's 0. It's because you forgot the salt bridge. If you want the volt to change, you need to get the ions to move from one spot to the other. So the salt bridge, it separates the two cells, and we call them components. Okay, you can call them cells too. And it allows the migration of the cations and anions. We need those cations and anions to move around. Now, how do they move? Well, the cations always go to the cathode. I always remember cat to cat. And the anions always go to the anode. So the an to the an. So inside here in our picture, we need to draw our salt bridge. And usually they will tell you what salt is in this bridge. And it doesn't even have to be any ion that's in common with this. So I've seen many times that they say KNO3 is in the salt bridge. So I'm just going to put SB. Okay, so KNO3. Automatically, as soon as this starts, first step, when it starts, the ions in the salt bridge migrate first. Yeah, migrate first. Okay, so as soon as you hit start. So what happens is you got to remember that the cations will travel to the cathode side, and the anions will travel to the anode side. Okay, just remember cat to cat, and to an. So right here, KNO3, strong electrolyte, strong electrolyte. So I'm going to get my K plus, and where's K plus going to be going? Well, here's Mr. Cathode. He's going to be traveling in here first, and he's going to be going into the solution. So eventually, I'm going to get some K plus in here. And my NO3, which is negative, well, he's an anion, so that means he's going to be traveling in here, and eventually, I'm going to be having some NO3 pop in here too. But then what happens is over time, the other ions will migrate. And what ones am I talking about? I'm talking about these two red ones, the N plus and the C plus. The question is, which one will travel through where? If they're both positive, both cations, who's going to be traveling in? Because not both of them will, only one of them. And because he's a cation, he'll start to get sucked up this tube because it's full of gel. He'll eventually get sucked up and he'll start to travel, and eventually you're going to get some N plus 1. And oh, look, he's attracted. He's forming some precipitate also. And that's how the cathode's mass increases. You're going to see a wonderful video of this in just a couple minutes that will even make the understanding even better. Okay? So what about anions? Let's just say maybe there's like some Cl minus in here, okay? Maybe some bromide, maybe some nitrate, whatever. Eventually over time, because he's an anion, he's eventually going to get sucked up and start to travel the other way too, okay? So just remember, ladies and gentlemen, how they travel through there, okay? But you need that salt bridge. This was an AP question that completely bamboozled students because they didn't read it. And I'm going to show you exactly in class where it is, okay? So students, when they read it, they didn't read about as soon as you turn on the voltmeter, it asked them which ions, to draw it in the picture, which ions were traveling in which direction. The students were looking at the ions in the beaker. But it said in the story, as soon as the cell operates, okay? So when they say that cell first operates, it basically means when you turned it on, as soon as you turned it on, it's only the ions in the salt bridge that migrate first. Okay, it's so important, ladies and gentlemen, that you read the questions correctly. All right. The migration to ions maintain electrical neutrality. And if the electrons flow, where do they flow? Well, they got to flow through a piece of wire. So in our picture, what we would usually draw is you would see like a piece of wire, and it's got to touch the electrode. And probably in the lab you saw these things called like alligator clips. If your fathers or uncles or grandfathers ever did anything with electrical stuff, they look like kind of like little clips, but they're called alligator clips. And this in between it is called a voltmeter. And we finally got some super duper cool ones to play with, and they're sitting in a box right now in the classroom, just waiting to be used. So this voltmeter obviously measures voltage. So this is our brand new unit coming, Mr. Capital V. And the electrons are migrating through here, but which way do the electrons always migrate? And that word always, from the anode to the cathode. So you're going to see like in the AP Daily video, she shows that the electrons are going this way, and she doesn't even tell you who's the anode or the cathode. One's aluminum, and I think the other one's like zinc or something. If you know where the electrons are traveling, then you know who's the anode, because the electrons have to flow from anode to cathode. And they're just going to keep on going, and that's how it also gains mass. Standard cell notation, you may see it written like this, but this is not something that's tested on the AP test, so I'm not going to worry about it. Okay, you just may see it like that on like a homework problem or so, but I'll get to it. Voltmeter is how we measure it. It's the actual piece of equipment, the device of how we measure it. We also call it cell potential. Now this is going to be big because we're going to talk about this in 20.4. And the units we're going to use is Mr. Capital V. Big, big V, because little v is velocity. So Mr. Capital V. So in here, we're going to do a sample one with zinc, and we're going to do one with copper. Okay, so right here, oxidation, lost electrons, and see, this is where the electrons appear on the product side. And over here, this is reduction of copper, and on this side, the electrons on the reactant side. And you want to make sure, ladies and gentlemen, your equation is balanced. I have a +2 charge right here, and I have 2 electrons, which means that's -2. And that's how it equals 0. Same thing on this one with the copper one. So in this picture, if you notice the zinc right here, remember where's oxidation, and that's the zinc. So this is my anode, my piece of zinc metal, and this is my copper piece of metal. And inside here, I have some zinc +2, and I have some copper +2. Now, I don't know who the negative ion is, and I really don't care who it is. But in this salt bridge, who's migrating where first? Well, Mr. Potassium +1, potassium's going to migrate to the cathode side, and Mr. Chlorine minus, he's the one that's going to be migrating to the anode side. Okay, I'm going to teach you how to do this calculation. Okay, and it's a very, very, very simple calculation. Like I said, we're not going to do cell potential. Okay, so if the zinc is the anode, what do we know? Well, over time, it'll eventually just start to, I don't like to say the word disappear because it doesn't disappear. I'm definitely going to be editing some notes. The zinc will eventually just continue to lose mass. He will appear to be shrinking, but he won't completely disappear because the zinc electrode is losing mass because it's losing, electrons. And the zinc concentration will start to increase. Now, this is very important, ladies and gentlemen. Remember these pieces of solid that's on here? This zinc solid is going to start turning in to zinc concentration. So because of the solid is transferring, we're losing him. The ion, we're going to start to gain him. So you're going to see this value just start to increase, increase, and increase. The concentration will change. Okay, it kind of sounds like we are messing with concentration. There must be some concentration coming into this. The copper will eventually, these ions will start to plate on here and start to just keep increasing this mass. And what you're seeing now is the opposite. Now the ions are going to start to transfer and make precipitate. So your precipitate will start to increase. And that's because the mass is increasing. So your concentration will be decreasing because you're producing more solid and less ions. Okay? As I said, I'm going to teach you how to do this calculation on the next video. So I included this section years ago because it helps students with all this kind of information thrown at them, all the different parts. It's kind of like an in conclusion, in summary. Redox reactions have to be thermodynamically favored. They have to be. Because if they are not positive... All right, ladies and gentlemen, sorry about that. Little guy's friends came to the door to play. Isn't that cute? Redox reactions are always spontaneous. So your delta G needs to be negative. But what you're going to see is this new letter coming in, a capital E, little degree sign. It's got to be positive. Okay? That's the voltage. So that volt, those electrons that are going through the wire on that voltmeter, it's got to be positive. Okay? So when we measure this, well, we'll put on this one. This, for it to be a thermal dynamically favored reaction, that what's called it's called E cell. Sometimes we call it EMF. So right up here, as you saw right here, cell potential EMF, that's what we're talking about. It's got to be positive. So when we do the calculation for delta G, it will be negative, okay? So this E cell right here, we can measure it with the voltmeter. And then when we do the calculation, that delta G will be negative. And you'll see that calculation in 20.5, okay? The two pieces of metals, those are electrodes. I mean, this is just one big, giant, big star, okay? The two pieces of metals, those are electrodes. The electrons always, 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 always flow from anode to cathode, okay? The anode is always negative, and the cathode is always positive, okay? So that's why I always make this a list, so that way I can remind myself, okay, what did I need to label? So according to our picture up here, the anode is always negative, and the cathode is always positive, okay? So if you're going to get electrons to move, these electrons right here, remember these electrons are negative, they're attracted to the cathode side, okay? Remember, opposites attract, okay? That's why they flow that way, and it'll always do that because it's spontaneous, okay? The laws of chemistry says opposites attract. It will get attracted to the positive side. That's why it's thermodynamically favored. The electrons cannot flow through the solution. That's big, because when AP has you guys like label stuff like this, you won't draw one from scratch, but heck yeah, they'll have you label stuff. You don't put the electrons going through the liquid. The ions are going through the liquid. The electrons are through the wire. Only the ions can go through that salt bridge. Okay, so only the cations and the anions. The cations will always go to the cathode side, okay, to neutralize the excess negative ions. Okay, that is very big. The anions will go to the anode side. And why? Because they're trying to neutralize the excess positive ions. Okay, opposites attract. The anode will have electrons on the product side. Okay, so when you do your equation, you will see the metal, arrow, positive, with the electrons on the product side. And then the cathode, you would see the electrons on the reactant side, and it gained an electron. Oxidation occurs at the anode. Cathode has electrons on the reactant side, and reduction is at the cathode. The flow of electrons from anode to cathode, it requires that wire. Okay, like I said, one big giant star. I've had students over the years think of mnemonic devices to help you. I mean, obviously Leo, the lion, Gur, he's out there in the world. I mean, the guy on AP Daily already took my Leo the lion. Oil rig has been around for years. I'm not even going to lie, I did not invent that because it's even in the textbook. Okay, so oxidation involves loss of electrons. Reduction involves gaining electrons. I've seen an oxidation anode, red cat, reduction cathode. I've even seen a student say fat cat. So from anode to cathode. I thought that was pretty genius. The electrons will always go from anode to cathode. Okay, whatever mnemonic device helps you, ladies and gentlemen, you do what you got to do. Okay. This next 2 pages, this is called U and drawing, okay? Tyler DeWatt, I love his explanations. You saw him in honors. I think he does a fabulous job explaining chemistry in a simpler way, okay? And let me show you where his videos are. So right here under Rodriguez videos, if you go to the next page, this very first one right here, Introduction to Electrochem, you're going to be labeling and drawing to help your understanding of this, because it's this one lab. It's like titration. God, I wish we could do this. If I could pick just 2 labs for us to do to help, it would be this one and the titration one, because it really makes sense when you physically can see the precipitate form on the cathode and how the anode actually starts to shrink over time. So you're going to watch this one. That's why I gave you a whole solid page. And I don't mind if you cut and paste pictures, ladies and gentlemen, but you got to make your own notes. And then the next video, the Voltaic cell. And he does very good particle diagrams. So Marlene, you're going to love it. Beautiful, big particle diagrams. And it's going to be in that second video right here, galvanic cells. Okay, so that's the diagram that I'm looking for right there. Okay, you may have to pause and rewind a couple times to help your 20.4. See you on the next one.